Good morning, ladies and gentlemen, and welcome to the SAIEE Nuclear Chapter webinar on small modular reactors, a review of status of light water projects. Before we move on to a few webinar considerations, you are reminded to ensure the volume is turned up on your device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. You're welcome to ask questions via the questions panel located within the GoToWebinar control panel. And by default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other, however, are encouraged to ask questions. A recording of this webinar will be made available on the SAIEE YouTube channel, SAIEE TV, under the Nuclear Chapter playlist. The registration link is in the chat box. Please register so you can receive updates and notifications. It is free. A certificate of attendance will be issued a few days after this webinar. I'd like to introduce you now to our host and presenter, well, our presenter today, Mr. David Nichols, who's the chairman of the Nuclear Chapter and was appointed as a chairperson of the board of the South African Nuclear Energy Corporation in January 2020. Prior to his retirement at the end of December 2018, he was the Chief Nuclear Officer at Eskom. Internationally, Mr. Nichols was the chairman of the IAEA Technical Working Group on Light Water Reactors from 2010 to 2016, and is currently the co-chair of the IAEA Technical Working Group on Nuclear Power Plant Operations. He was a member of the WANO's post-Fukushima design review team from 2012 to 2018. Over to you, David.
Thank you. I'm now going to do my normal thing of, I'll do a quick bit of screen share. Come on, where am I screen sharing? I've got a problem with the screen. Oh, yeah. Show my screen. No. Show. Sorry. Okay. Is that visible? Am I okay?
Yes, we are. Perfect. Please proceed.
Okay, thank you. Okay, right. This is one of the first of 4 webinars we're doing, the Nuclear Chapter. We're doing one a month, largely because everyone's talking of small modular reactors. It's a fashionable thing, but people often don't quite know what it is and what status of projects there is. So my aim today is, and we're going to do one session on light water reactors. That's what I'm doing today. There'll be a session in a month's time looking at gas core reactors. Then we're going to look at molten salt, and then the last one's going to be the other, I call them weird and wonderfuls. So let's start. So what I try to go to today is, what is a small modular reactor? What are the kind of design options? If you start with a clean sheet and say, I'm going to build a light water reactor, small modular reactor, how would I actually go about it? What are the issues I've got to choose on? And then the advantages and limitations of water-cooled reactors in this field. And then the main part of the talk is going to be on going through about 9 of the current designs that are out there in the world, and just discuss where they are and what their global issues are. So with that, I will start with what is a small modular reactor. Small modular reactor is defined as a reactor between 3 and 300 megawatts, although some of the reactors I'm going to show you, one of the reactors I'll show you a bit later is bigger than that. And it's worth bearing in mind that if you go back to about the mid-1990s, I know this well, there was a view in the nuclear industry that the only credible reactors were 600 megawatts plus. In other words, anything below 600 couldn't be commercial. So what are the features of a small modular reactor, and why are they that way? The first thing is that a lot of the developments are looking for what's called inherent safety. In other words, no not all are going that way, but that was the fundamental start starting point. And the aim of that is to increase public. Okay, I'm back again. Sorry, I appear to have disappeared for a few seconds. Apologies, you can blame probably load shedding and so one of the big drivers of nuclear was the increase in nuclear safety costs, which went to. Third one is small unit size. It is increasingly recognized that the mere financial risk and exposure you take by ordering a $5 or $10 billion project with a 10-year lead time is extreme. And even if the costs are slightly more, if the unit size is smaller, your exposure and your financial risk is a lot less. What's also interesting is that the technologies, if you go back into history, there was in the 1950s and 60s, there were many technologies out there that were developed to a certain point, but were essentially abandoned because of a degree of, we all went down to one design. So we've ended up going from probably a dozen different technology designs across the world, which are all very credible, down to a single one, which is the pressurized water reactor. And the reason we've gone down to that is, and the reason that was chosen is a lot to do with politics, industrial policies, who was good, had good management, who had bad management, and so on. The next issue that SMRs have across them is an increasing drive to operating flexibility on both cycle length and load follow. In other words, the ability to run the plant at any power you want to at a cost-effective manner. And so the idea is, again, to link in with renewables more than a big reactor like Kubo, which tends to be run full blast all the time. And the last one, which is probably the dominant one in reality, is absolute standardization with high unit volumes to maximize learning effect. In terms of materials used, a small modular reactor will logically be less cost effective than a bigger reactor because of the economies of size scale. But the reality is that the savings by building a large number of standard machines is greater than the value you get from having a large unit. This is something which is a long discussion in its own right, but is increasingly being recognized. And what this means is, so where are we now in the development program of small modular reactors in the world? This is a graph I quite like. I found it somewhere. I think it's, I forget who it came from now, so I apologize if I'm stealing someone's IT. What it says is who gets involved in developing things. At R&D level, it's almost always government. And then there's that valley of death where you need to put more money in to get to a certain point. And that valley of death, that is the fundamental research valley of death for almost all SMR technologies, and particularly for the water-cooled reactors, has already been done. No one's really questioning the technology of many of these projects. But the real killer is the need to move from a very good design, when the government's doing less and less involvement, to a point where you're building a commercial lead machine. And that is the problem that every single, well, virtually everyone I'm going to show you in a second of the designs out there is sitting here with a real challenge of getting past this commercialization valley of death. And to put it in simple, for a light water reactor, in my opinion, to get the economies of scale, you've got to have both the first machine largely completed and a firm order book with production ongoing for the next 5 or 10. Then you can start getting investors on board. But the investors are very happy to invest when you get that done, but they're much less happy to invest to get there. And then lastly is just when you build it. What this probably means is that in all the SMRs in the world, I estimate there'll be probably 3 to 5 of them that actually come to become real commercial machines in the long term. Most will fall by the wayside, not necessarily because they're a bad design, but because they can't get past these valleys of death in terms of needing money from an unknown source. What this does mean, and you'll see it in the next few slides, is that the reactors that are developed by countries where they have a very strong link between their industry and the government, and that will clearly be someone like China or Russia, is best placed to overcome that commercialization problem. And that could be the real problem, that the free market ones haven't got the depth of pocket as the developer to do all that, building the first machine. Okay, So what are the options? I'm now going to design a light water reactor. How do I actually build one? Well, the first thing I'm going to decide is, do I have integration or distributed components? And what I'll explain that by is, if you look at a classical reactor like Coburg, you have got a reactor pressure vessel with the core, you've got a pressurizer attached to it, you've got separate pumps, you've got 2 loops to steam generators, and all this is spread out in little components, distributed. The initial driver for the light water reactor option is to integrate all that into one vessel. And you have certain designs I'll show in a second, which are fully in one vessel. And this, so the one vessel becomes markedly bigger, but you end up with, in many ways, a simpler system. One of the reasons why integration was highly fashionable, but is now becoming less fashionable, was that integration, if you look at the safety codes for nuclear reactors, you will find that it is presumed that pressure vessels do not fail, but pipes can. Therefore, making an inherently safe water-cooled reactor, if you can make the pressure vessel big enough and put everything inside it with no pipes, then you have no serious prospect of a large break loco, as we call them. And therefore, you've got a much better safety. But of course, this is also based fundamentally on the problem that the assumption that the pressure vessel can't fail is a good assumption up to, let's say, 10 to the minus 5, maybe even 10 to the minus 6 per year. When you start talking about safety standards that go beyond that, then your vessel failure becomes a challenge. The other problem that hurts them is that the size of vessel becomes very large. One of the advantages of water-cooled reactors is that they have quite good power density, and therefore the pressure vessels are quite small. That was the argument in the 60s between the water-cooled reactors and the gas-cooled reactors. But the problem with that in this discussion is that if you build a pressure vessel big enough to have enough thermal inertia in the water, then you actually end up with a pressure vessel which is the same sort of size as the gas-cooled reactor. So that's the first question I make, which we're doing. The second one is, how much do you try and make the plant factory constructed? In other words, you don't do any construction on site, you build everything in the factory, ship it to site, plonk it down. Extreme case, some reactors are planned to be 100% built in a factory, fueled in a factory, and delivered to site as a fueled item. And then when the refueling is required, the whole reactor is taken away some years later. That limits your size. There are 2 reactors I'll mention when you go through the RollsRoyce one's example, where their reference point is their only criteria is that every component has to go by LOE, and they'll build the biggest reactor they can inside that scope. So factory construction is a big issue. 100% factory construction is clearly not possible, but also, so what scale on that one do you go? Third one is, how do you get your safety? And this is the classical discussion between active, which is you've got active motors and pumps driving pumps, passive, which is what you have, and active is the classical Coburg type safety system. Passive is more the AP600, AP1000 type design, where you don't actually have any pumps and valves, but you have tanks and you have natural siphoning to provide cooling. And the last one's inherent safety. And inherent safety of a water-cooled reactor essentially means your RPV is big enough that you don't, that as long as the RPV doesn't actually have a catastrophic rupture, you actually end up with enough water to keep the plant cool for time. So those are, and the third one is, what fuel cycle do you go? The fourth one, sorry, what fuel cycle do you go for? In my opinion, there's interesting discussion because a classical fuel cycle, because one of the problems with a light water reactor is we don't have on-load fuel handling. So your fuel, you put the fuel in, button the lid down and run it. And you've got, the shorter your fuel cycle, the less capital you have tied up in your fuel, but the more refueling outages you have. So there is a move. So you can look at the range, and I tried to all the reactors, one I couldn't find the number for it. All in other words, what is their design fuel cycle? And clearly, the shorter the fuel cycle, the lower your fuel cost will be, but then also the lower your availability will be. The longer the fuel cycle, the higher your fuel cost will be, because you're storing all that fuel in the core for a long time, but the more availability you'd have. And there is a move on the smaller reactors to move to a state where essentially you end up with the refueling being very unusual. Of course, the extreme case, blunt, is if you go back to nuclear submarines and nuclear aircraft carriers in the world now, they're building them in a 25-year course because they don't want to go near it. So those are the kind of options you've got. There are other options, but those are the kind of discussions you're going to make. And you'll see as we go through the designs coming up that different designers have gone different ways. So why would I go for, what are the advantages of going for a water-cooled SMR versus a gas-cooled or a molten salt or anything else? Well, the first one is absolutely clear. The technology base for water-cooled reactors is fully proven, demonstrated. In other words, in all these designs with incredibly few connections, you're buying from an existing supply chain. You've got what you'd know exotic materials. You can get it. You can do a safety case. There's no real uncertainty in will the material work or not. The other point about water-cooled reactor is that because you've got a good cooling system, there are no obvious power limitations. And we know this because you can take a water-cooled reactor and you can make a water-cooled reactor at 1,500 megawatts, and you can do it with the same technology you're doing for the SMR at 50 megawatts. So those are the four advantages. So that's but there are some limitations. The first one is that you've got both the high pressure, you've got to keep at about 155 bar pressure, and your pressure boundary has to have high integrity because your safety case says I don't leak or don't leak too badly. So both your pressure boundary and potentially your containment building have to have high integrity. There were other designs, which I will go in the next few months, which have high pressure. Gas-cooled reactors have high pressure, but it isn't a high integrity pressure boundary. If a pebble bed reactor loses its coolant, it doesn't worry it too much. It may not make power anymore, but it won't be unsafe. So it's a combination of a high pressure, very high quality, high integrity, and therefore expensive pressure boundary. Again, comes back to if you go for an integrated plant, your pressure boundary becomes a massive cost issue. Second one is low temperature cycle. You're dealing with water and the boiling point of water, and essentially you're constrained by thermodynamics to about 300 degrees centigrade as a top process heat you can generate. Not too much of a problem with power generation because we're used to that and we can get reasonably good efficiency out of that. Not quite as good as higher temperatures, but the real thing is if you want to use this as a process heat application, there is a range of applications beyond 300 degrees centigrade where this cannot be used. And next limitation is that nobody's bringing up a light water reactor with on-load fuel options. Therefore, you've got shutdowns every 18 months to 8 years, should we say. When you shut down, take the core out, put the core back in again. That is a constraint. It is something we live with in the industry, but it's not actually ideal. And the last one is, it's the only design that's being put forward at the moment which has two-phase coolant. And I say it's got a safety constraint because clearly what water can do as water is very different to what steam can do as steam. So this two-phase coolant gives you the problem, which again brings you back to this leakage problem. So that's sort of the advantages. The biggest advantage is very simple and it's very straightforward. It is fully proven, existing supply chain, no exotic materials. No one's questioning the ability to build these machines. Okay, so what have we got in the world's field at the moment? I've chosen these. There are a couple others out there which I haven't chosen, but I think this covers the vast majority. And I'll go through each one in turn. I start with the three that are actually in construction today. You can go to the site and you can see them doing work on these plants. One's the RITM in Russia. I'll discuss it in a second. I'll present these all in turn. It's in construction. ACP 100 in China in construction. Korean 25 in Argentina in construction. Note the asterisk because they've had several stops to construction because of financial problems. To put it fairly, Argentina has got economic problems that even we would worry about as this country. So they've got a major financial crisis, and that's an example of that valley of death in that the money is not available to them to actually build the first lead machine. NuScale Voyager is the USA, I would say, is the USA's leading contender. It's got design certification in the USA. All of these, except for the next one, are pressurized water reactors of some kind. In other words, they've got separate cycles for the steam cycle and they have for the nuclear cycle. The GE BWRX 300 is in fact a boiling water reactor. It has a contract to build 4, and they're starting very early site work in Canada for that. AP300 from Westinghouse in the USA is a cut down version of an AP600. I'm going to design a term and just go through one, so, and I'll try and be reasonably quick. I will comment that in many cases the information on them is quite limited. Lots of sales brochures, but actual information is limited. So let's look at first one, LIT M200N. It's a 55 megawatt electrical. It's an 8-year fuel cycle. The reason for the 8-year, and this is the longest fuel cycle anyone mentions. It's in construction, Yakutia, which by the way is in far eastern Siberia, but it's based completely on an existing Russian design. It's a fully integrated machine, and it's part of an extensive small modular reactor program. The Russians have built nuclear icebreakers with very similar reactors. That's what the KLT-40S came from. They've extended it and idealized it, but you can see the bottom left-hand corner is actually a picture of, and I can't even pronounce the name. This is the Russian barge that's up in far, far eastern Siberia and was built in St. Petersburg and then dragged round. It's easier to build the thing in Siberia and drag it round than to build it in St. Petersburg and drag it round to Siberia. That's got 2 reactors. I think they're about 35 megawatts each. It's a precursor to these. The new icebreakers they're building have very similar machines, and the new machines coming out now that are being built as standalone power plants outside the grid system. So this is by far the most. If you want to go and order a nuclear reactor today in the small reactor thing, then I would suggest to you that the Russians would take an order from you in the morning if you go and knock on their door. The 8-year fuel cycle is because they don't want to have to maintain the refueling systems out at these remote sites, so it would be very rare event. And in fact, their floating proposal is that 8-year fuel cycle, and you take the barge back to Russia, and you get refueled in Russia. So that's the first one, very realistic. This, by the way, this is the design, integrated design. There are your 4 pumps. There's your water in, steam out, limit stage of control rods. This actually is them casting, forging the first RPV for the Yakutia plant. But that's a very serious program. The Russians are very serious. Complete fuel cycle, the whole 2 thing is organized. The next one is the Chinese, ACP 100. It's also called a Ling-Along 1, I think. 125 megawatts with a 2-year fuel cycle. It's in construction. There's a photo in construction in Hainan. It's meant, which is the extreme west of China on an island on just the south coast of China. It's on an existing nuclear power plant site that has 2 600 megawatt machines, and it essentially is a cut down version of a large reactor. So it's a classical containment building. You can see from the diagram over here, it's got classical makeup tanks, emergency core cooling systems, very similar to a sort of AP1000 type, VVR 1200 type passive systems. You can see that the AP1000 approach to the cooling is there. That's going to go online. Should load fuel the end of this year, go online next year. Very serious, very credible project, and is 125 megawatts. It's the reactor that the Chinese, when they came to Africa for a conference 3-4 months ago, this is what they were pushing very heavily as a reactor for Africa. And it's, you can see it's integrated reactor. So there's, you can see my mouse is visible. Right. There's the core, and these actually are the steam generators on the site. So you've inside integrated, not fully integrated like some other designs, because the pressure, I think the pressurizer is outside the container, the pressure vessel side. So that's the next one. The next one, the construction is actually the absolutely classical small modular reactor, fully integrated steam generator, the nuclear steam generator, the pressurizer. It's Carine 25. It's a 1-year fuel cycle. It's in construction on the Atusha site in Argentina. The commercial will be 120 megawatts. This is not the commercial machine. This is the proof principle. And it's been in construction. They poured concrete in 2014 on this one, but it's been delayed extensively because of contractual problems, because not paying bills has been an issue, to put it mildly. Standardized design, again, the safety case is basically that the RPV will not fail, and therefore the worst you can have is a small steam line break. Interesting discussion that the safety is based upon, if I can call it cynically, the codes and standards saying RPVs can't fail, which is true at, let's say, 1970 safe standards. If you're looking at inherent safety, you're looking at -8, and you can't, it's difficult to prove that. So that can be a challenge for that one. But it's there, it's real, it's in construction today. There are workers on site working on that plant. But its problem in the Valley of Death discussion I had earlier is that there, with the first two I showed you, China and Russia has massive state funding backing it. And therefore, you want to buy one, they will back you up with financing. I'm not sure Argentina can do that. So it's going to challenge this one. Okay, we've now been through all the ones. So if you're talking about water-cooled reactors, small modular reactors in construction, that's it. Everything from here on is a function of good paper. So the next one I have brought is a new scale Voyager reactor. It's 77 megawatts electrical, 18-month fuel cycle. It has NRC design certification, and basically that's the reactor. You can see the reactor there. Same sort of design as the last one. You've got the fuel at the bottom. You've got essentially close to natural circulation, driving the water around it. It's very credible design, and it was going to, they were going to build it, and it all sits in operation. They all sit in a pool of water. So their ultimate heat sink is this big pool of water they're sitting in case of loss of everything else. So looks pretty good to me. The only issue is that they had an agreement to construct the first unit. I mentioned you got the first block of 12 in Utah, supported by some government guarantees. And the first of class costs started going up, and they had several other potential orders to be after the first order. Again, you know, I'll always buy number 2, but never number 1. And that first order was then cancelled because of cost issues in the States. And so they're now struggling to find another launch customer. They're talking to Romania. They're talking to the Ukraine. The Ukraine is signing for several reactor designs, but I'm not sure they're going to get to build them because of their other problems. But this is a very credible design. Having design certification does not mean it's buildable. I'll be honest about it. The reason you'll see a first one built is not because the design is fundamentally flawed, but because only when you build it, you work all the little details out. And that's what causes problems. So that's the Voyager. Moving on. This is the odd one out in a sense that it's a boiling water reactor. You can see it's a very classical boiling water reactor. Control rods on the bottom. There's your fuel. There's your water. There's your dryers. And it's a 300 megawatt with a 2-year fuel cycle. Ontario Hydro has ordered 4 units. I'm very wary of turning from ordering to actually constructing. They're clearing the site. It is a simplified BWR design. It's at the basic design stage. So the first 3 I've talked about, the first 3 have done detailed design because they're building them. The design certification NRC requires a fairly large amount of detail in the process. This one is at the basic design level, in my opinion. It is interesting because General Electric originally had a simplified boiling water reactor, which was 600 megawatts under the EPRI program in the 1990s. Same AP, and that was then abandoned as being too expensive. They then went to build the ESBWR, the Economic Simplified Boiling Water Reactor, which was 1,500 megawatts, and nobody bought that one. And so now they're going back to the marketplace with 300 megawatt version. And Ontario Hydro in Canada has ordered 4 on the Darlington site, so they're clearing ground now. Should be going forward. Very straightforward design, well understood. It's just basically a small version of a boiling water reactor with standardization. Okay, next one, another one on the same line. Westinghouse recently announced the AP300. It's got a 4-year fuel cycle. It's got single loop. It's basically a single loop of the AP1000 design. So if those who know it, the AP1000 has 2 big Gs and has a power level of 1,000 megawatts. Westinghouse has now announced that they're now going for a 300 megawatt version of the same thing, which essentially is a single loop design. There's the pressurizer, there's the tube generator, there's that pressure vessel that I presume is the pressurizer, and it's got the same safety systems as an AP1000. So the advantages, and a system that needs to be fully licensed, it's been fully qualified, and therefore the design, I suspect, is at a basic level. So in other words, they've got all the components defined, haven't got the manufacturing sorted out yet, but that should be straightforward because they're versions of the systems used for the AP600. And now, I would almost expect this to get bigger in due course. In other words, there's no reason not to make an AP400 where you end up with a slightly bigger SG and then it becomes bigger. Hence the fuel cycle, I suspect the core is close to the size of a standard 900 megawatt plant, which would have an 18-month fuel cycle. So you've got less power coming off and less fuel. But it's there. It's so far just been announced a few months ago, but I think it's very serious because Westinghouse is a very serious player. Next one, also USA, HTech. HTech is an engineering company in the States which is extremely competent. It's doing the spent fuel casks for Coburg. It's one of the big manufacturer states of spent fuel casks and things. And this design is interesting. It's a 300 megawatt design, and it's basically was originally built, as you can see, it's a distributed design. Here is the pressure vessel, the fuel. Here is the steam generator with a pressurizer above it. So it's sort of a restructured, and there's a control that drive. It's a restructured version of a normal reactor. It was originally planned as a 160 megawatt reactor, so the SMR 160 until about 6 months ago, and it was planned to be natural circulation. And then somebody commented that if you put pumps in design, increase the flow. So it's about now. HTech has a very good reputation for very practical engineering, and again, they're very much a credible engineering company in the sense they're not. They've done a lot of work, not quite as much as building a reactor. What is really interesting is that they have bought the Palisades nuclear power station, which was recently shut down at end of life. They bought, and so they intend to build themselves for themselves 2 units to the Palisades site. I haven't mentioned other people in the previous ones talking about future orders because I'm a bit wary of people having wishes. What's interesting is HTech has also applied to the NRC to restart the Palisades reactor. In other words, they bought the reactor with this decommissioning fund to decommission it, and that was going to be cost effective. And now they're suggesting they should restart the Palisades reactor and build 2 more units of this on this site. It's certainly at basic design level. I think maybe we're slightly ahead of that. It's highly credible because of the company running it and because of their philosophy. Okay, getting close towards the end of the discussion now, and then we can open for questions. The UK RollsRoyce, and we've got no name for it, it's called the SMR. And this is the one which is not 300 megawatts, it's 470. And just a bit of background on RollsRoyce, you know where they come from. RollsRoyce is a company that is the supplier of nuclear reactors to the UK submarine fleet. So they have a lot of experience, but it's not been commercial in the nuclear field. And they're now moving into the civil nuclear field. So clearly they understand boiling water pressurized water reactors very well. What they've done here is they've issued a specific. They said they were going to build a plant where the criteria is not megawatts, but every component must be shippable on the back of a lorry. So you've ended up with a 4-loop, 470 megawatt reactor. You can see the 4 loops there, with each with its own pump, with a separate pressurizer. So it's a classic, it's a shrunk version. All the other ones are slightly clever versions, either completely integrated. This is the one which is totally old school layout and being driven on a supposedly commercial basis. To be honest, this is the best. This is probably a very neat replacement for the VVR 440s that were in Eastern Europe, and I believe is a highly credible machine. But again, It is one of 6 reactors, most of which are on the list already, which the UK is looking at as their world of SMRs. So very much a very conventional, very much a straight off the shelf machine, it's in the process of the UK GDA, which is Generic Design Approval Process, which is the UK version of design certification, and it's at system design level now. But again, it's had some money crises. It's had recent things of hasn't got the money to develop these things. Those valleys of death I said earlier, you know, getting past the hump and getting the investment. The order books come when you've proved everything. The money comes to prove everything. Okay, my last one, and I've been going for about half an hour, so this will be my timing is not bad. It's Nuart. This one is actually 170 mega electrical. They basically have got the design is for 2 reactors in a pair, so 340 megawatts, but they're 170 megawatts reactors. It's at concept and system design level now in France. EDF is driving the process, a lot of the companies involved. They've declared their design of the first concrete in 2030. And what you can see in this diagram is how they've engineered it. That middle part there, you can just see in the RPV, contains all the components that the pressurizer, the steam generator, everything is in there. That sits inside a containment shell, and you can see the access hatch containment shell. What's interesting is that there are 2 of these containment shells inside one very large tank of water. And its passive cooling system, which is these here, is in fact essentially the same as you have on a nuclear submarine. And I know that's my own background, which is interesting because clearly in the French nuclear industry, they build nuclear submarines. So what someone's done is they've taken the basic nuclear submarine passive cooling system and replaced the sea with a tank of water and this is the submarine if you think about it. Well, that's a sensible idea. Clearly some way to go before they get there, but it's very credible as a way forward. Okay, that I think leads me to the end of my presentation. So I'm now open to any questions. I hope I've been come across clearly. Yeah, any questions? And I'll be very happy to answer any questions.
Yes, I see we David, thank you so much for your presentation. I don't see any questions in the questions panel yet. We give the attendees a few minutes or a few seconds to just type a question in the questions drop down menu on the control panel, and then David can answer that for you. While we wait for your questions, if you look in the chat box, there's a few links how to become a member of the SAIEE. It gives you more information. Our upcoming training academy calendar on our website, as well as the March issue of What Now that you can download in PDF format. And as mentioned before, the registration link to the SAIEE TV channel on YouTube. We have a question here from Walter Moewa. Thank you, Walter. Yeah. He's asking, can SMRs used to produce power for local municipalities?
Yes, in fact, and it's not water cooled. In generically, what I believe we are looking with SMRs, they got so big they end up being a national scale project. And I was talking to AMEU actually yesterday, Valley Pariachi, because my view is that what you can do with an SMR is you can go back to what we might call the town power station. What happened historically was we got bigger and bigger plants, large in South Africa, largely coal plants, and therefore they're cost effective on the coal fields, which went where the towns were, and therefore we end up with the national grid being created. I don't see the national grid going away, but I do see the point of literally Joburg, for example, potentially buying SMRs to put on the Kelvin power station site to generate the power for the Munich. And again, that's one of the reasons that you want small plants, because if you end up replacing, let's say, so you put a 1,000 megawatt machine on Kelvin, which you could do theoretically. Your problem is that when that machine is down and you've got to refuel occasionally, you've lost all your power. If you put 10 100 megawatt machines on Kelvin, the council could manage that much more straightforwardly. So the SMRs do open up the prospect of the town power station. And then the grid merely becomes a bit of a trading activity between them. It isn't feeding it. So yes, I think that this is absolutely one of the options on the table to do that. Okay.
Thank you. We've got another question from Nolofefe in Galangkulu. My apologies for the pronunciation. Seeing the different OEMs for these SMRs, how is the market for the fuel? Is it limited to each reactor type or can be interchanged or interused?
I think we're going to see that in the large reactor space, in pressurized water reactors, we've come down to 3 designs of fuel out there, essentially. You can buy fuel from multiple suppliers. But they all started out as a VVR fuel. It's the old combustion engineering 16 by 16 fuel assemblies and the Westinghouse 17 by 17s. I think you're going to find that the SMRs will all start out with their own version of the fuel. And I think that what we're going to see is, as I said earlier, I think we're going to get maybe 2 or 3 of these designs to actually get rolled out sensibly. They will initially get the fuel as part of the package from the supplier, because by nature the SMRs are being sold into smaller companies who aren't going to get involved in fuel manufacturing. And I think we'll end up with a standardized fuel for a fleet of SMRs, and you may get multiple suppliers for that way. In the same way at the moment is if you want to buy fuel for Coburg, although it's a Westinghouse designed fuel, Westinghouse supplies the fuel, or Framatome, or the Russians, or the Chinese, all those make fuel that fits the whole. So I think it's going to start out as a OEM-based fuel supply, but I suspect they're going to end up then with other vendors getting into the fuel business over time. But certainly at the beginning, when you buy your first SMR, it'll come with the package from the SMR supplier. I think it's one of the problems, and it's not so much a problem in these reactors because they're very much, again, the fuel may not be the same physical size as fuel assemblies for a light water reactor, but the technology is going to be the same. So if you go to a fuel plant, you can build it. Whereas when we talk about more advanced reactors, the molten salt, the lead cooled, the gas cooled ones, you're going to find the fuel there is not like anything's being built today. Again, proven supply chain.
Thank you, David. We've got another question, a follow-up question from Walter Mulva. He says, can SMRs be used as part of a smart grid solution, pairing them with renewables? How easy are they to be synchronized with other power sources?
Actually, there's 2 answers to this question. The one is technically it's dead simple. Nuclear plants can inherently load follow better than fossil plants. That may sound odd, everyone thinks the way around. But nuclear plants, Coburg, for example, has a bigger power range than any ESCOM coal station. But the problem is that because in a nuclear plant, your fixed cost, your capital operating and maintenance are very high, and your fuel cost is very low, then on the what's called the merit order, it's the last machine you unload. If that makes sense, because you don't save much by not running it. So at a technical level, if you want to force renewables into the system, then nuclear is a perfectly good carbon neutral, net zero carbon balance for that. The problem economically is that if you think about renewables and a backup power system, it's a fundamental view of economics, but if I'm going to build a renewable fleet for the country, clearly at some point the sun is not shining, the wind is not blowing. That is very true. We don't want load shedding, so you end up having a backup system, which must be available 100% of the time to meet essentially 100% of the load. So you've got 2 cost elements. You've got the renewables and you've got the backup. But the backup, if the backup has very small fuel costs, then the renewables are actually competing with the fuel cost of the backup. That makes sense. In other words, if I've got a natural gas power system, my natural gas is, my fuel cost on my natural gas in today's numbers cost me £1, let's say. Then clearly, as long as the renewables come in at below £1, which they do, then simply you whenever the renewables running, you're saving money on gas. The problem is that if your backup power is nuclear, and your fuel cost like Coburg is about 7 cents, then you've got to get your then unless you can get the total cost of the renewables below 7 cents, then why build them? Just build the nuclear and run it. And that's the problem with this matching. So technically, there is no problem. You could link Coburg will be an excellent plant. Coburg is an excellent technical plant to go with renewables. It can load follow beautifully. And in fact, you can build reactors with much more load following than Coburg. I mean, I use the obvious example. For those who know my background, I was in nuclear submarines back in the 70s. And the original PWR, and nuclear submarines can load follow like you don't want to. They can go essentially 0 to 100% power in about a minute, and they can go from 100% to 0 instantaneously without tripping. It is very flexible. We never thought about load following as an issue on a submarine. So you can build them. And SMRs are much closer to that than to the big Coburg type reactors. But the answer is, if you can load follow, why don't you just take the whole grid and make it all nuclear? Why are you building the renewables? Unless, of course, you've got interest in renewable shares. Sorry, withdraw that comment. Back to you, Minx.
Thank you, David. Yes, we have another question from Johnson Sabelo Maseko. He's asking component replacement and refurbishment considerations. Does it come with localization?
I think, and I'm asking a wider question than just water-cooled reactors, but the answer is, if you build enough of them consistently enough, you will build a local industry. So if someone said to me, we are going to replace the coal fleet of 30,000 megawatts on the Highvelds with nuclear plants, with small modular reactors of 100 megawatts each, that's 300 reactors. You will build the local, you can easily build a local industry out of that process. So the question on that one is, yes, of course we can do it. We built components for Coburg over time. I know that at Ellendarbus, Safari is entirely supported by local industry. So there is no stopper in that process. It's a question of, do you buy enough for it commercially viable? If you buy one SMR, you will not get a localization industry going. But that's another of the joys of SMRs, is the components are fundamentally smaller lumps, therefore easier to build, and a lot more of them. So if we were to build 5,000 megawatts of SMR, that would be, I don't know, 30, 50 reactors. That means, for example, you can quite straightforwardly localize that, even if the design is not local.
Thank you,
So, yeah,
David. Thanks. Another
big target for us.
Yeah, Johnson has a follow-up question. What are the environmental considerations for these type reactors?
The honest answer is that everybody is aiming, and almost all regulators are demanding, that we have no off-site emergency planning issues. So there's two environmental, I do this kit. In terms of releases, in terms of radioactive releases, there is not an issue, as there isn't really with Coburg, but these are better. In terms of cooling water, you could run people forget that we run largely dry cooled power stations in South Africa. So if somebody said water is a shortage, then we could build these, because there's a thermal, all of these have water cool, classical Rankine cycles. Same as Matimba does, same as Medupi does, same as Kendall does, same as Kusile. So you could put dry cooling on the back of them. So water isn't an issue. The fact they're water cooled isn't an issue, because you don't lose that water. That water stays well looked after, the actual primary circuit. The second one, in terms of the emergency, of the safety issues, the emergency evacuation, and everything else, is these plants, and the standards nowadays are that these plants should not require any emergency planning activity offsite. And that's very much the situation, and is fundamental to making them viable. Again, that's why you could talk about Kelvin. You would have massive problems, I think, politically with it today if we're going to put nuclear power station on Kelvin. Everyone would complain it's too dangerous for Joburg. But the reality is the safety standards are now at a level where there's no logical argument for that. I hope that answers the question.
Thank you, David. We seem to have, there's no more questions. So I'm sure that we can call it a day for this very informative webinar.
Thank you.
I thank you very much for your time. And David, thank you for your presentation. And ladies and gentlemen, thank you for your time. We thank you, and please look out for the advertising collateral for the upcoming, the next webinar, as David mentioned, on gas cool SMRs. Thank you very much for your time, and happy Easter to all. Have a good afternoon further. Goodbye.
Thank you all. Thank you.